So, how do we measure the properties of stars? With very few exceptions, we don't see details of stars. They're not star-shaped. We assume they're round like the sun. We have to analyze the light from the stars then in ways that the naked eye can't. So those tiny glints of light in the night sky are in reality very huge, dazzling balls of gas, many of which are vastly larger and brighter than the sun. They look dim because of how far away they are. Now, we can't probe stars directly. We can't go and make a measurement or dip a cup in to take a cup of star matter and figure out what it is. So we have to come up with indirect methods to ascertain their properties. Measuring distances to stars and galaxies is not easy. And distance is a very important number for determining lots of the intrinsic properties of astronomical objects. So one way of determining distance is triangulation, where we would measure a triangle, and so we have a baseline, and then we have maybe a 90-degree angle, another angle, and if we know a baseline and two angles, we can figure out the distance away something is. We use trigonometry or a scale drawing to determine how far it is. And in astronomy, we can use trigonometric parallax. So, for example, the stars that are really, really far away will not move depending on where the Earth is around the Sun. They're too far away. But a star a little bit closer will actually look different. If you take your thumb and hold it out at arm's length and close one eye and put it over some object in the distance or on your wall, now switch eyes. Now, your thumb appeared to move against the background stars. It didn't really move, but because of parallax, because I'm looking at it from slightly different places, it changes its position on the background. We do the same thing here. We'll take a picture of the sky and we'll look at a star here in January, and that star will appear to be here in the background. Then 6 months later, when the Earth is on the other side of the Sun, we can look and it appears to be somewhere else. And I can measure the angular distance of the two places it looks like in the sky. If I know that angular distance, this angle here will be half of it. My baseline is 1 astronomical unit. That's a big baseline. This is a 90-degree angle, and now I can determine how far it is from our solar system to that star. Again, looking at it from above, you can see this right triangle a little bit better. This is called parallax. The baseline is Earth's orbital radius, and angles are measured with respect to very distant stars. The shift of nearby small stars is really small. The angles are actually measured in arc seconds. And the parallax angle, P, is half the angular shift of the nearby star, and its distance in parsecs is given. A parsec is a unit of distance that we use for stars close by to us. It's 3.26 light years. It's kind of the average distance between stars in our neighborhood. Now, parallax is really only useful to stars that are about 250 parsecs or closer. So we can even look at an example. Sirius is also known as the dog star, and it's one that's fairly close. And we can see the parallax angle for it is 0.377 arc seconds. And remember, an arc second is a 60th of a minute, arc minute, which is a 60th of a degree, which is 1 over 360 degrees around a circle. So from the formula, the distance, you don't need to know this formula. It's 1 over the angle, and it's 2.65 parsecs, or Sirius is about 8.6 light years away. Another method for determining distance is called the standard candle method. Now, if an object's intrinsic brightness is known, its distance can be determined from its observed brightness. So, in other words, if we know how bright a star is from some other method, and we know how bright it appears, we can tell how far it is. You could do this in a lab too. If I knew I had say a 100-watt light bulb, and I put it at some distance away, I took another 100-watt light bulb and I put it close by, and a distance I could measure. I took a photograph of it. The diameter of the circles of on the picture of the light from that, the ratio of that would be the same as the ratio of their distances. This is actually the principal manner in which astronomers determine distances in the universe. So light is the astronomer's tool. We want to know motions, sizes, colors, and structures of stars. This information helps to understand the natures of stars as well as their life cycle. The light from the stars received at Earth is all we have available for this analysis. Now the color of a star indicates its relative temperature. Blue stars are hotter than red stars. More precisely, a star's surface temperature in Kelvin is given using Wien's law. Remember, we look, and the maximum brightness of, if we look at all the different wavelengths, the ones that's the peak tells us something about the temperature in Wien's law. So by just looking at what color is the maximum brightness, we can determine the temperature of a star. Now, luminosity is a property of a star that tells the amount of energy it emits each second. And luminosity is usually abbreviated with a capital L. A typical unit of measurement for luminosity is a watt. So, a 100-watt light bulb tells you its luminosity. The sun's luminosity is 4 times 10 to the 26 watts, or 4 million billion 100-watt light bulbs. Luminosity is a measure of a star's energy production, or in other words, how fast it's burning hydrogen fuel. So knowing a star's luminosity will then allow us to determine the star's distance and radius. The inverse square law relates an object's luminosity to its distance and its apparent brightness, how bright it appears to us. The law can be thought of as the result of a fixed number of photons that once the photons come off the object that's giving light, they continue to go out. So they spread out evenly in all directions as they leave the source. So then the photons have a larger and larger concentric spherical area that they go through. So for a given shell, the number of photons per unit area decreases. If I think of this light bulb here, and I have, say, 36 photons coming through this 1 meter square area at a distance 1 meter away, those same 36 are now spread over, when I'm 2 meters away, over 4 square meters. So now there's only 9 photons per square meter. And I have the same number of photons going through all of these, but the area that they are spread out over is getting larger. So the number of photons per unit area decreases. The inverse square law then, it becomes the brightness of an object is its luminosity divided by 4 pi d squared, where d is the distance away from the object. This relationship is called the inverse square law because the distance appears in the denominator as a square. The inverse square law is one of the most important mathematical tools available to astronomers. Given, say, distance from parallax measurements, a star's luminosity can be found, because a star's brightness can be easily measured by an electronic device called a photometer. We can connect it to a telescope, measure its brightness. Once we know its distance, we know its luminosity. However, the real power to this becomes if I know the luminosity in advance due to something, and I can measure its brightness, I can then calculate its distance using the inverse square law. Now another thing we might want to know is radius. So let's use some common sense here. Two objects of the same temperature but different sizes. The larger one radiates more energy than the smaller one. Just imagine if I had, say, a BB and a large cannonball, and I put them in a fire and they're glowing orange hot, and I take them out. The larger one is going to radiate more light. It's going to be brighter. They're the same temperature, but the larger object gives off more light. In stellar terms, a star of larger radius will have a higher luminosity than a smaller star at the same temperature. So how do I know the luminosity in advance? First, we need to know how much energy is emitted per unit area of a surface held at a certain temperature. There's another law in physics. I'm just letting you know how this works. The Stefan-Boltzmann law. You don't need to know how to use it, just that it exists. It says the brightness of an object is equal to some constant, that's the Greek letter sigma, times its temperature to the fourth power. Now the Stefan-Boltzmann law applies to stars, but not hot, low-density gases. We can combine the Stefan-Boltzmann and the inverse square law then to get that the luminosity is 4 pi r squared sigma t to the fourth, where r is the radius of the star. Now let's look at this. If I know now the temperature from Wien's law, and I know the luminosity somehow, I can now find how big the star is, or its radius. So putting it together, I have the total energy radiated per second by the star as its luminosity. That's the energy emitted by 1 square meter times the number of square meters on its surface, which would just be sigma t to the fourth times the star's surface area. And if it's a spherical star, the surface area is 4 pi r squared, so that's how I get this all together. You do not need to know how to derive or put these equations together. I just want you to see how a scientist uses fundamental laws that they can determine, and they start to combine them to be able to use them to measure things that you wouldn't think that you could measure. By looking at energy output and temperature, I can figure out a radius. Now, the methods using the Stefan-Boltzmann law and interferometer observations show that stars differ enormously in radius. Some stars are hundreds of times larger than the sun, and we call those giants. And others are smaller than the sun, and we call those dwarfs. So for example, the same star we were talking about before, Sirius, if we solve for the star's radius, it can be simplified if we apply this equation to both the star and the sun. It's another thing that scientists like to do. Instead of having to solve each thing, we just take the equation for one, divide it by another, and we can get a relationship between things just by looking at ratios. And if you do, you can get this equation. It says the radius of a star over the radius of the sun. That symbol, a circle with a dot in it, is the mathematical symbol for our sun. So this means the radius of the sun, the luminosity of the sun, the temperature of the sun. We use our sun as a astronomical unit of different things. So for Sirius, we know that its luminosity is 25 times the sun's. It's 25 times more energy output than our sun. Its temperature is 10,000 K and the sun was 6,000 K. And therefore you put that together and we find that the radius of Sirius is 1.8 times the radius of the sun. Now another way of looking at stars is something called magnitude. And in 150 BC, Hipparchus was a Greek astronomer, and he measured the apparent brightness of stars using units called magnitudes. The brightest stars in the sky had a magnitude 1, and the dimmest had a magnitude 6. Now this system is still used today, and units of measurement are called apparent magnitudes to emphasize how bright a star looks or appears to an observer. This would be the brightness. A star's apparent magnitude depends on the star's luminosity and distance. A star may appear dim because it's either very far away or it doesn't emit much energy. Now apparent magnitude can be confusing because the scale runs backwards. It's a logarithmic scale. High magnitude means low brightness. And modern calibrations of the scale actually create negative magnitudes for things like the moon and the sun. Magnitude differences equate to brightness ratios. So a difference in 5 magnitudes is a brightness ratio of 100. Now all these numbers down here are just based on logarithms. It's a logarithmic scale. So astronomers use absolute magnitude to measure a star's luminosity. The the absolute magnitude of a star is the apparent magnitude that same star would have at 10 parsecs. A comparison of absolute magnitudes is now a comparison of luminosities, and there's no distance dependence.